Okay, well, yeah, if you have any questions about the test, please feel free to come talk to me about it. I'd be happy to talk about it. And if you want to talk about study strategies, you feel like things aren't going the way you want, I can talk about that. Yeah, just come talk to me. So now we're going back to conservation of mechanical energy. And I'm just going to do a few example problems. And I'll do a spring problem or two. Okay, so first of all, let's say that we did one last time where somebody was on a skateboard at the top of a hill and you saw how fast they were going at the bottom. Let's sort of turn that around and let's say that you have somebody, let's say that this is snow, and we're going to assume that there's no friction. And so you have this skier that's going along the flat at the bottom of the hill. We don't know what speed they're going, but let's say that we want them to be at the top of the hill, and let's say that this has a height of 1.5 meters. For the skier, to be moving 5 meters per second at the top of that hill, how fast would the skier have to be moving along the flat? Okay. Well, the first thing you have to make sure of is you have to make sure that this is eligible for conservation of mechanical energy. So let's think about what forces are acting on this person at a sort of representative moment during this problem. So here's the skier. There's a weight force. There's a pushing force from the ground. We're going to pretend that there's no friction and that there's also negligible air resistance. So this is the complete free body diagram if we're making those assumptions. So now let's think about those forces and think, can we use those? Well, weight is a conservative force. We have a potential energy function for that, so that's fine. The normal force is a non-conservative force, which could be a problem, but the question is, does it do any work? A normal force during rolling or sliding is one of the two forces I told you about that is non-conservative, but it does zero work. So this is fine. We can use conservation of mechanical energy for this problem. All right, so now that we know we can use it, let's divide it up into a first instant and a second instant. Instant 1 is going to be while the skier is moving along the flat. instant 2 is going to be at the top of the hill. Okay, so the only potential energy we need is gravity, because that's the only conservative force we have. So what's the skier's gravitational potential energy at the bottom of the hill? I said this is what I always do. I just take the lowest point in the problem and call that my height equals 0. You can choose any point you want as long as you're consistent with it, but I just always choose my lowest point. So the potential energy due to gravity is the mass of the skier times 9.81 meters per second squared times the height, which in this case is 0. So the gravitational potential energy is 0. And then the kinetic energy is 1/2 times the skier's mass times the speed squared. Do we know what the speed is at the flat?
5 meters per second.
The 5 is at the top. So we don't know what it is at the flat. That's what we're trying to calculate. So we'll just leave that in as V. Okay, so that capital V is what we're going to try to calculate. And now we'll go to the top of the hill. The gravitational potential energy is the mass times G, which is 9.81, times the height. If height equals 0 is at the bottom of the hill, the height at the top of the hill is 1.5 meters. So this is 14.715 m. And now the kinetic energy at the top of the hill is 1/2 times the mass. Do we know the speed at the top?
That's 5.
That's the 5, yep. So times 5 squared. So that's 25 divided by 2, 12.5 times the skier's mass. And now we can put this stuff into conservation of mechanical energy. So we have 0 plus 1/2 m v squared is equal to 14.715 times m plus 12.5 times m. Both sides, everything's multiplied by m, so we can just divide both sides by m. And we get 20, over here we get 27.215. Over here we get 1/2 v squared. Multiply both sides by 2, and you get v squared is equal to 54.43. Now take the square root of both sides. Can someone do that for me?
Yeah.
7.3776669.
Okay, so 7.38 meters per second. And this is a speed, so negative doesn't mean anything, so we want the positive one. So if this skier is going 7.38 meters per second at the bottom of the hill, at the top of the hill, the skier will be going 5 meters per second. Any questions about that? What if the skier weighed 50, question?
So the mass isn't the 9.81.
That's right. That is the lowercase g. and then you multiply that by the mass. And what we saw is that the mass disappears from the equation, which means that this answer would be the same no matter what the skier's mass is. So if the skier had a mass of 10 kilograms or 100 kilograms, that speed would come out the same. Any other questions about that? One thing I want you to notice that we're starting to see, and this is just sort of a general fact about conservation of mechanical energy, is what are some hints that you can use this? So hints that conservation of mechanical energy is the way to go. Okay. Well, the first one is, so we can only do this problem when the forces are in that group of 5 forces that I listed. So that's the first one. The forces only include gravity, spring forces, so we'll get to a problem or two like that. Normal forces in rolling or sliding. And then the last one is centripetal forces in circular motion. Well, if you have any forces that aren't in that group of 4, then we haven't talked about how to use this approach. So first look for that. And then the second thing, the second hint that you should use is notice that conservation of mechanical energy problems always relate an object's location to its speed. Okay? How fast is this thing moving at the top of the hill? How far down the hill can this thing go and have a certain speed? So you can only use this if you're looking for a relationship between an object's location and the object's speed. Okay, let's do another example. This is a continuation of one I did a while ago when we were talking about circular motion. So let's say that we have this thing again. Somebody's holding onto this string, swinging a mass around in a circle. Okay, and gravity is acting this way. So this thing is rising as it goes up. Let's say it's going this way. Falling as it goes down the left side there. Let's say that this string has a length of 20 centimeters, 0.2 meters. And the mass is 0.1 kilograms. So first, let's figure out the slowest, the mass can be moving at the top of the circle to maintain this circular motion. Bless you. We've done a problem like that before, so this might look familiar. Second, given that this mass is the slowest that it can possibly go to stay in this circular path, let's figure out what's the corresponding speed at the bottom of the circle. And then third, let's figure out what the cable tension is. Okay, this problem is gonna combine a few different things. We're gonna use some circular motion stuff, some Newton's second law stuff. For part B, we're gonna use conservation of mechanical energy. And you can see that what we're doing is relating the speed of an object to its location, so it makes sense. Okay? So basically what we're doing is figuring out how strong that string has to be if we're going to go the absolute slowest we can and still have this mass move in a circular path, this circular path. Okay, so first, for part A, we're going to look at the top of the path. And let's think about the free body diagram at the top. There's a weight force that's equal to 0.1 times 9.81, so 0.981. And then there's also a cable force. What direction would the cable force act when this thing is at the top of the circle? Yeah, right, down. Because it's parallel to the cable, away from the body, so it would be that.
Same direction of gravity.
Same in this case, yep. When we later do a free body diagram at the bottom of the circle, it'll be opposite gravity. And so Newton's second law says 0.981 negative plus 0 negative t is equal to the mass times the acceleration. Well, I haven't done this yet, but let's think now about I always say to do it in the opposite order. I'm sort of switching things around. But here's our circular path. Okay. And we're figuring out what's happening with the object. It's actually not there. It's here, right? The centripetal acceleration then is toward the center of the circle. So there's the centripetal acceleration. The magnitude of that centripetal acceleration is v squared over r. Do we know what r is?
Radius?
Yep.
0.2.
0.2, right. And so the centripetal acceleration vector is 0 negative v squared over 0.2. Well, that's our acceleration, so now we can put that in here. So this is 0 negative v squared over 0.2. Okay, so if this is going the slowest it can possibly go and stay in this circular path, do you remember what we said? So we can't solve the y component of this equation the way it is right now because we have a t and a v. But if it's going the slowest it can possibly go and still stay in that circular path, do you remember what simplification we made now? What we said is that we're going to find the speed that it's going to make that t equal to 0. Okay, so that's the slowest that it can go without falling out of that circular path. Remember doing a problem like that?
Yeah.
Okay, so the y equation now says negative 0.981 plus 0 is equal to negative 0.1 v squared over 0.2. And we can write that as 0.981 is equal to, what's 0.1 divided by 0.2?
1 divided by 0.2, 0.5.
0.5, yep. So we got 0.5 v squared. And so 1.962 is equal to v squared. And so can you calculate the square?
1.4.
So v is equal to 1.4 meters per second. And it's positive because it's a speed. Okay, so that's the slowest this mass can be at the top of the circle and still stay on the circular path.
You just take the t out.
Yes, what we said is so if it's going faster than this, then that cable has to pull on the thing to keep it in its circular path. If it's going slower than this, in order to stay in that circular path, the cable would have to push on it to keep it in its circular path. Well, we know strings can't do that. So we're finding exactly between those 2 points. And that's the point where it just makes it around the circle, when that cable isn't doing anything. Okay? But it still has this centripetal acceleration. So in other words, it still stays in a circular path. Okay, so that's the speed at the top of the circle. Now we're trying to figure out what the speed of this ball is at the bottom of the circle. We're trying to find that corresponding speed at the bottom of the circle. Well, let's think about a representative free body diagram, So at some point between the top of the circle and the bottom of the circle, you'd have a cable force like this. You'd have a weight force of 0.981. So let's think about, are we able to use conservation of mechanical energy in this case? The weight force is conservative. We have a potential energy function for the weight force, so that's fine. What about this cable force? We don't have a potential energy for that, right? This is non-conservative. But notice that this cable force is always acting toward the center of the circular path. Okay? So the work is equal to 0. Because this is a centripetal force. So we can use conservation of mechanical energy. Does that make sense on this one? Okay, so let's write out this table. we have instant 1, that's at the top of the circle, and instant 2 at the bottom of the circle. We have to choose a height equals 0. I'm going to choose the bottom. Okay. So at the top of the circle, what's the gravitational potential energy? It's the mass times 9.81 times the height. The mass is 0.1 times 9.81. What's the height at the top of the circle? The radius of the circle is 0.2, so the diameter from the bottom to the top is 0.4, okay? So this times 0.4, and so we get 0.3924. And the units of energy, anyone remember the units of energy?
Joules?
Joules, yep. And the kinetic energy at the top is 1/2 times the mass of this thing, 0.1, times the speed squared. Well, we calculated that the speed is 1.4. So we have 1.962, 0.1962. I think this is 0.0981. Can someone calculate that?
I didn't get the 1, but maybe 0.
Okay.
Yep.
And it's negative 3 should be. Oh, it's equal.
Yeah, right. And now at the bottom of the circle, the gravitational potential energy is the mass times 9.81 times what's the height at the bottom? 0, yep. And the kinetic energy, we're trying to figure out the speed, so this is 1/2 times the mass times v squared, and we'll solve for that v. This one's joules. So conservation of mechanical energy says 0.3924 plus 0.098 is equal to 0.05 v squared. Can you add those two?
.4904.
0.49, I'll just round up, 0.490 is equal to 0.05 v squared. Now divide both sides by 0.05. Can you do that division? So v squared is equal to 9.8. It's really 9.81 if we hadn't been rounding and stuff. And then take the square root, and I think you get,
3.13.
yeah, plus or minus 3.13 meters per second. We want the positive. Okay, so if this thing is going the slowest it can possibly go and stay in the circle, it's going 1.4 meters per second at the top of the circle. It's going 3.13 meters at the bottom of the circle. The bottom of the circle is where that string is likely to break. That's where the string is under the most stress, okay? So now we're going to do a circular motion analysis at the bottom of the circle and figure out what that cable force is. Okay, so here's the circular path. There's the point that we're interested in. The centripetal acceleration is toward the center, so that way. The magnitude of the centripetal acceleration is v squared over the radius of the circle. That's 3.13 squared divided by the radius of the circle, 0.2 meters, which is 9.81 divided by 0.2. So I divided by 0.2, that's 49.05. Now put that in its vector form. The centripetal acceleration, you can see it's in the positive y direction, so this is 0, 49.05. I sort of glossed over this on part A and part C, but what about the tangential acceleration? You always have to think about the tangential acceleration in circular motion problems. Well, remember from lab, we've seen this a few times. There are 2 points on a circle like this where the speed isn't changing, exactly at the top and exactly at the bottom. So at both of those two instances, the only acceleration we have is centripetal. Okay. All right, so now we can go to Newton's second law. Well, first, I guess, draw a free body diagram. So we have the weight this way, 0.1 times 9.81. A cable force away from the body, so that way, toward the center of the circle. And so Newton's second law says 0t plus 0 negative 0.981 is equal to the mass times the acceleration vector, which is 0, 49.05. The y equation says t minus 0.981 is equal to 4.905. And so t is equal to 5.8 87.
I guess that's 5.
4.905 plus 0.981.
Did you want to add it? Oh, you added.
Just add, yeah.
10.88.
886. And there you go. That's how strong the cable has to be for this 0.1 kilogram mass to be swinging around in that circle. If the string is not strong enough to support that tension, it's going to break when the ball gets to the bottom of the circle. So that's sort of like, that's a problem where you're just taking a bunch of the different things you know how to do and combining them into a single problem. How would you make this problem harder? Really, it would make this problem considerably harder if I just didn't tell you to do A and B before C. If I just said calculate the cable tension, you'd have to think through being able to figure doing all this just to get down to the cable tension. It's just easier here because I sort of walked it through. Okay, let's do a spring problem. So let's think about a mass oscillating on a spring. So let's say we have a little cart here with a mass of 0.2 kilograms. And it's connected to a spring that has a spring stiffness, K, that's equal to 100 newtons per meter. So the way you would do that is so if that's the spring with no force applied to it, the way you'd come up with this spring constant, if you apply a force to it, it'll stretch, right? And so you take this force that you apply to it, you measure how much this spring stretches, and then that spring constant is equal to the force divided by the stretch. So like, for example, maybe we applied, to get this spring constant of 100, let's say that we applied a downward force of 1 Newton, and we saw that the spring stretched 1 centimeter. 1 Newton divided by 0.01 meters gives you a spring constant of 100 newtons per meter. Okay, so that's what that spring constant means. And you can imagine that number would get higher the stiffer the spring is, because if you have to apply 1,000 newtons of force to it to get it to only stretch part of a centimeter, that's a really stiff spring, and you'd get a really big value for that K. Okay. So now let's say that you pull this mass to the left 0.01 meters and release it. What'll happen is that mass will oscillate back and forth, okay? Sometimes it'll be going slower and sometimes it'll be going faster as it oscillates. And we want to calculate what's the fastest this cart will be going. So what's the fastest speed during that oscillation? Okay, well, first we have to think if we can use conservation of mechanical energy. If you ever see a spring in a problem, we haven't talked about springs any other way except conservation of mechanical energy, so that's sort of a giveaway to you that that's what you're going to use. But it's a good habit to think about whether we have everything we need for this. So what are the forces that are acting on this cart?
The spring and gravity,
Yeah, that's exactly right. Gravity, normal, and the spring. So there's a weight, there's the pushing normal force, and then there's the force from the spring. It would sometimes be pulling on it, sometimes be pushing on it, but it's like that. This one is conservative. We have a potential energy function for the spring, so that's fine. Gravity is conservative, so that's fine. The normal force is non-conservative, but the work is equal to 0, so that one's fine too. Okay. So now we know we can start filling out the table with the two different instants. So instant 1 is going to be when it's released. Instant 2 is going to be at some arbitrary position. Okay, so we're just going to represent its position with variables. Okay. All right, at instant 1, and let's take the height of this thing we'll call that h equals 0. You can see then, since the height is never changing, the height is just going to be 0 at every instant, right? Okay, so at instant 1, the gravitational potential energy is mg times the height of 0, so it's 0, right? What about the spring potential energy? That's 1/2 times k, which is 100, times how far is this thing moved from its resting position?
0.01.
Yeah, 0.01. So, and the formula says we have 1/2 times k times 0.01 squared. So that's 50 times 0.01 squared. Can you tell me what that is?
0.005.
Okay, so 0.005, and that's in joules. And if we're pulling it back and releasing it, we're releasing it from rest. So the kinetic energy is 1/2 times the mass times the speed squared, so 0 kinetic energy. And now let's think about these values at some arbitrary point during this oscillation. Okay, so the gravitational potential energy, what's the height at some arbitrary point during the oscillation?
0.
Still 0, yep. Then for the spring, we'll just say that the displacement is x. Okay, so this is 1/2 times 100 times x squared, or in other words, 50x squared. And the kinetic energy is 1/2 times the mass, 0.2, times the speed squared. Okay, so conservation of mechanical energy says 0 plus 0.005 plus 0 is equal to 0 plus 50x squared plus 0.1 v squared. Subtract 50x squared from both sides. you get 0.005 minus 50x squared. Hold on a sec. Okay, 0.005 minus 50x squared is equal to 0.1 v squared. Divide by both sides by 0.1, so you get 0.05 minus 500x squared is equal to v squared. Now take the square root of both sides and you get v is equal to plus or minus, we want the positive because we're looking for a speed, square root of 0.05 minus 50x squared. Okay, so for a given x value, for a given distance from the resting length, this is the speed. Where is this speed going to be? You know, what x value is going to make this speed biggest? We have a number and we're subtracting a positive number, so the biggest this can be is when x is equal to 0. So what that tells us is the speed is the square root of 0.05. What's the square root of 0.05?
0.223.
0.22, I'll leave it like that, meters per second. And what's the stretch or compression of the spring when it's at its fastest point?
0.
0. It's when x is equal to 0. So that means that if you stretch this spring, it'll speed up as it gets toward the spring's resting length. It'll be at its fastest right as it's at its resting length. Then it'll slow down as it compresses, and it'll keep doing that process. Every time it passes the spring's resting length, it's going to be at its maximum speed, this. Okay, well, I'll do more spring problems next time, but that's a first one. Any questions? Okay, that's all.